introduce Giuseppe Gaeta, whose title I've lost, Free Energy According to Poincare and Landau.
Okay, so I hope this works. You have been telling things about the latest development, but I will tell you things about a bit older things, if I can manage to start it. I will speak about the work of Poincare, and you know this guy. It's Landau in an uncommon picture, and Louis Michel, which at least somebody in the audience knows. But I, contrary to Randall, I had troubles with slides and pictures. So it will be a talk without pictures. There is something going wrong in my computer. I could not mix the things. So what is the problem? I wanted to tell how the work by Poincare at the end of the 19th century, actually in his thesis, could be useful for liquid crystals. This is the plan of the talk, more or less. And what is the problem? In Landau theory, what we have to do is to find the minima of an effective potential, the Landau potential. And this potential depends on parameters which govern the phase transition and so on. The Landau potential is characterized by the symmetry. And more or less what we have to do, well, we all know what to do, so let me just say quickly, is that we represent the state of the system by a number of order parameters, and we should expand the potential, namely the most general potential with some symmetry properties, up to some order, and truncate this potential in this order, and then see what happens, namely what are the minima depending on the parameters. The order usually is chosen the smallest possible order so that the potential is convex at infinity, so it's stable, but on the other side to allow for phase transition, which basically means well, I will say later what it means. So what is the problem with this program? The problem is that except for textbook examples, in general, you get very complicated potentials, just a big number of coefficients. And then it's a mess. If things depends on 104 coefficients, then it's difficult to analyze, but already if they depend on 22 coefficients, it's a mess. So what is the problem? What is the idea? The idea is that it would be nice to be able to simplify the potential somehow. How can we simplify the potential? There are two ways. One is that to find a different potential which has the same physical properties. The other is to express the same potential in different coordinates. So the first way, I would say, is a physical way to drop the irrelevant terms, which should not be confunded with what is irrelevant in renormalization group approach. And this, in the words of Arnold, there was the art of throwing away in essential terms of Taylor series, retaining the higher order but physically important terms. I stopped the quotation here, but he was saying that this was given to high degree of art by Landau and his collaborators. The second part is, of course, much more dull, and that is what I will speak about. You don't need to be Landau to change coordinates, luckily. So Poincare, what has to do Poincare with this? Poincare worked on his thesis on a problem which is related to this one. What was Poincare's problem? Just be a moment of patience about something different. So he considered a vector ordinary differential equation with having an equilibrium at the origin. And he wanted to linearize this. At that time, people thought that everything could be explicitly solved. Then Poincare realized that this is not always the case. Well, okay, I'm of course just saying things a bit more simply. And the idea was to expand this in series around the origin, so you have a potential. And then you try to find coordinates in which at least the lower order, but in principle all the order, the nonlinear terms can be cancelled out. Or now we know that it's not always possible, at least can be simplified. So what was the idea of Poincare? The idea was to do it step by step, order by order. It's maybe not surprising that it turns out that it's not possible to kill all the nonlinear terms, but the nice surprise is that we can find out, well, Poincare could find out what is explicitly the obstacle to do this. And why is that possible? Because at each step, the transformation working in perturbation is controlled by a linear operator. So linear operator is the only case in which we can do something. The linear part was controlled by a matrix, and this matrix can be just put in journal normal form, as we teach to first-year students. So there is the semi-simple part is diagonal, and I will just assume that the nilpotent part is not there. Anyway, if you have a gradient problem, it's always like that. So the criterion to be able to solve the problem, so to kill the nonlinear terms, can be expressed in terms of these eigenvalues, and is that there is no resonance. A resonance is some relation of this kind between the eigenvalues, where m are non-negative integers, which sum up to something bigger than 1, because in case this is just 1, you always have this, of course. What is the trick? The trick is just to consider a near identity change of variables. Then, of course, how does this transform? Well, you expand in series at first order, and you get something like this. If this Hm is homogeneous, the terms of lower order, of course, are not changed. The terms of this order change in a specific way, which we'll see in next slide. And at higher order, there is something complicated. I don't care, because I will take care of this at next steps. So the idea of Poincare was not to care about higher things. And what happens at the order of the change of variables is that this changes as the gradient of h along the flow of the linear part minus the gradient of the linear part along the flow of h. So, but if this is this linear operator acting here, which tells you what is the new term, then everything which is in the range of this linear operator can be killed. On the other side, if I change with something which is in the kernel of the operator, I don't see anything different. And actually, this is relevant. I will not speak about this, but if you look at higher order effects of the change of coordinate, not just at the lowest order, these terms come into play. So at each order, we have to solve an equation like this. If we work in the right coordinates, things are nicer. And right coordinates, which means just take monomials of this form. And if you act with that operator I showed you before on things like this, you find that these things are eigenfunctions. And this eigenvector should be eigenvalue, of course. And this is the eigenvalue. So this also tells you why there is this non-resonance condition. Non-resonance means that this must not be 0. And if you have to solve the equation that we have seen before, you have to invert the operator, at least on the range of it. So you have basically to divide by this number. So if this number is small, you get what is called a small denominator, which makes trouble in the radius of convergence of the procedure. Okay, so this is what you can do in a non-resonant case. You can always invert this. Then a student of Poincare, Dulac, studied what happens in the resonant case. What happens is exactly the same, except that things that are resonant cannot be killed. Things which are in the range, which are in the orthogonal to the range of L0, they cannot be killed. So you remain with something which has nonlinear terms, but all these nonlinear terms are resonant, so are in this function space. And resonant, by the way, means that the flow of this generated by these things and the linear things commute. So this means that the linear part commutes with the full dynamics. This means also that there is no hope that this makes sense, that this is not just formal but convergent, unless there was a symmetry in the original problem. Because in the transformed problem there is a symmetry, so if it was not there from the beginning, you have been cheating somewhere. Where you have been cheating? Because you're working by series, and this is convergent nowhere because of this small denominator. Okay, then we don't really care about these things. These things can be extended to a Hamiltonian system. This was noticed just a few decades later. Birkhoff realized that if you work with Hamiltonian case, then you can work directly on the Hamiltonian, not on the vector field, which is simpler because you work just with one object, the Hamiltonian, rather than with an n-component vector field. And of course, this is the same if you work with the gradient vector field, as in Landau. In the Hamiltonian case, there is some trouble because there is always some resonance, which is due to this, but I don't want to speak about this. And there is then, if you take this higher order effect, which I was mentioning before, then you can arrive at a point where all the surviving terms commute among themselves. Of course, again, the Moser remark about the symmetry, this makes sense only for as many commuting terms as you had symmetries in the beginning. So at some point, you are sure that you will have to stop. After that, it will be only formal. Okay, this was just to say what is the general frame. But now the problem is, how can this be of use for us? So Poincare goes down. Now we come back to Landau. In Landau, we have this problem of a group invariant potential. And we want to simplify this. So I will assume that G is compact and it acts orthogonally in Rn. I don't really need that it acts orthogonally. This is just to be fast in the discussion. And the fact that it's compact on the other side can be relevant. I can ask a bit less. But if I have, for example, the irrational flow on the torus, that is the counterexample to nearly everything, then this is not true. But luckily, when we deal with crystals or liquid crystals, often the groups are orthogonal. So, first of all, there is this Hilbert theorem, which was already recalled in previous talks, which tells that if you look at the most general invariant potential, here again there is a mistake. Look at the most general invariant polynomial, actually. There is a version of this for C-infinite functions, but I don't need it. If I look at the most general invariant polynomial, then there is a basis of polynomials, and all the G-invariant polynomials of any degree can be expressed as polynomials in the basis of this basis polynomial, which are homogeneous of some degrees. So the most general phi invariant polynomial in the X can be expressed as a polynomial in the J1 JR. And with the hypothesis I made before, the basis is a finite basis. Now, if I choose a basis such that none of the polynomial can be written as a polynomial of the other. It could be written as a non-rational function, but none of them is written as a polynomial, and R is the smallest possible value, then I have what is called a minimal integrity basis. I think you use a slightly different notation, but this is the thing. And I will call this JA the basic invariance. Now, these invariants, they're required not to be expressed as polynomial of the others, but they could have algebraic relation. For example, the square of one is equal to the cube of the other. In this case, the basis we say is non-regular, while if there are no algebraic relation, we say the basis is irregular. So from now on, assume we have chosen a basis and we have ordered the degree in some way. Now, this I can nearly skip because it was recalled in several talks before. So I can work with this basis of invariance. So what really matters is the value of this basis invariant. And so I call the orbit space the space in which these take value. And this is basically the original space quotiented by the action of the group. If the basis is regular, this orbit space is a region of full measure in R, sorry, it was not a good choice of symbol. while in general this is just an algebraic, it's not even a submanifold, it's a stratified submanifold, but of smaller dimension. But the important things, anyway, is that an invariant polynomial, I can write this in terms of the basic invariance. So instead of evaluating a function from M to R, I can do that in 2 steps. I can evaluate the basic polynomials, and then I evaluate the polynomial of the polynomials. Now, in the Landau theory, we have to deal with the most general polynomial compatible with the symmetry. So basically, we don't care about the second step. We only care about the basis polynomials, because the second function, the function psi, from the J to R, is a completely general function. So there is nothing which we should say about that. And so here is the third character, which was Michel, stressing that basically we can work Landau theory in the orbit space. Now, this also gives us some hint about where we should stop the Landau expansion. Because we work in this orbit space, we have functions of this J, but we should be able to break the symmetry in all the directions in general. So we need that it's possible that the potential is, I never know if this is concave or convex, but points down, goes away from 0 in all the possible directions, but we want it to be stable, so then it must come back, which means that it must be at least quadratic in all the J. So we look at what is the highest order of the J. This was the R, and I have to go to order 2 of the R, which does not mean that I have to take only quadratic in the J, but this means that I have to go to this order. And the reason is allow for symmetry breaking in all the directions in orbit space. In the regular case, it's clear, it's flat things, I go in this direction. In the non-regular case, it could be possible that it's enough to go to lowest order, but since this would be a complicated discussion, so I prefer to make some muscular work, as Tudor was saying, and just stay with this criterion. Maybe I am doing more than was needed, but this is just trivial work rather than being clever, and I don't want to have to be clever because maybe I will not be able. Okay, so one remark I already made, but the other remark is essential, that some of these coefficients could pass through 0, because if they don't pass through 0, I don't have any phase transition. It was just stressing this fact that phase transition, Professor Longo was recalling, are controlled by the linear terms. So at least the linear coefficient must be able to pass through 0. So the next and last ingredient, technical ingredient I know, is this matrix which was introduced by Sartori, and it's just this. Take all the basis invariants, take the gradients of these basis invariants, and make scalar products among the two. And you introduce this in a matrix. This will show up in what I'm doing next, so it's better to have a name for that. Sorry, I forgot to say that this is an invariant. The gradient is a covariant. Scalar product of two covariants is again an invariant. So the matrix is clearly can be written in terms of the J themselves. Now, what should I do if I want to reduce an invariant polynomial? What I mean reduce? I mean kill some of the coefficients. I have less coefficients to control. Well, I remember of my old Poincare, and I make change of variables which are identity plus an homogeneous part. Okay, but this change of variables should not be arbitrary. I want to preserve the symmetry, of course, and I like to be that the H are gradient functions. These are not. This is not mandatory. Rainer was stressing before that sometimes you have some covariant which are not gradient of invariance. So things are simpler if this is the case, but from now on I cannot claim that I am doing the most general things compatible with the Poincare approach. But the formulas will be simpler, which is a good point. So I will have just H is the gradient of something. but h is G invariant, so I can write h as a function of the basis invariance, and then the gradient is the derivative of key with respect to the basis invariance times the gradient of the invariance. Okay, and then I should make my chain formula for the derivatives. What I get is this, that JA is written in the new coordinates as J alpha plus the Sartori matrix acting on this Q. What is this Q? Is the gradient of H in terms of the invariance. So in the vector which has this component here. Of course, this Q is subject to a cross derivative condition. Okay, now I know how the basis invariants change. But what I want to know is how it changes this Landau polynomial, which was written in terms of the basis invariance. Okay, then I make these things. I know how the J change, and how will this change? Well, I take this plus the derivative of this with respect to the J times the change of the J, which was these things that I've written here. Okay, this is generic for order m plus p, but we know from the initial slides about Poincare that what really matters is what happens at the same order. So indeed, at order m, what happens is this. Psi m goes into psi m plus these things, and this thing is a linear operator depending on the quadratic part of the Landau potential, so the part which is linear in the J, applied on H. We have again a linear operator, so you can play the same game that Poincare played. We can kill everything which is in the range of this linear operator by suitably choosing the H. So I repeat, what we do is we operate sequentially, step by step, order by order. At each stage, we choose the generator Hm. By this, since this is homogeneous, we are sure that we are not changing the lowest order term that we already put in good shape, and we control what happens by the action of this linear operator. Everything which is in the range of this operator can be killed. Everything which is in the kernel of this operator, no point in taking an H with components here. Albeit, at higher order effect, this will show up. Now, what was psi naught? Psi naught was the quadratic part of the potential. So it was a sum with certain coefficients which are given by the Landau potential of the basis invariants which were quadratic, which had order 2. So not all of them in general, but only some of them. So this L naught is actually these things, where this sum, the coefficients are 0 if the degree was higher than 2. So we know what it is exactly. This is if I just look for minimum of the potential. I should make a remark that if we look at the flow, the gradient flow under the Landau potential, as Argir was saying in his talk, then things are a bit different, because I should consider the transformation of the derivative term as well, and the formulas are a bit different. Okay, so this is the general scheme. I think I still have a few minutes. And let's see some examples. First example is just reflections in X and reflections in Y. I have, of course, only these two invariants. So the P matrix is this. This is the linear term, the quadratic term, sorry. The quartic term, there is no cubic term. The quartic invariant term is like this. On the other side, the general generating function at order 4 can also be written like this. I act with the L naught on this, and I obtain this. Okay, I can kill the coefficient of this, of J1 squared, because I have something. I can kill this because I have something. I can kill this because I have something. How can I kill them? Just by choosing P1, P2, and Q. And here is how I have to choose them. Watch out. I can do this if A1 is not 0. I can do this if A2 is not 0. I can do this if the sum of A1 and A2 is not 0. If I have a phase transition at some point, I'm passing through 0. So there is a trouble. Example 2, so in which case I have a non-regular basis. So I take inversions, again in 2 dimensions. So invariants are x squared, y squared, and xy. In this case, the basis is not regular because the product of J1 and J2 gives me the square of J3. So the geometry of orbit space is a bit, well, not really like that, but it's a bit more complex. I can compute the matrix. I write the quadratic term is written like this. The quartic term is written like this, depends on 5 coefficients. I have not written anything of the form J1, J2 because these are already in this part. The change of variables are generated by this. I make my computation and things, this is the change in the quartic term. This I can write taking a vector with components P, Q, with components again along each of these basic things of 5th order. This is a 5 by 5 matrix. So I can invert this matrix if the determinant is non-zero. I don't want to write complicated formulas, but I just want to show that everything is explicit. I can just make computation. Up to this point, maybe I could do that by hand. If not, I take my Mathematica and I build matrix. I just ask to compute determinants, invert matrix. Of course, if I want to invert a matrix 50 by 50, the computer will complain. But in principle, everything is explicit. Then this was the example which really motivated when I started to work on this, is something by Sergienko, Gufan, and Uratsdin, when they worried about perovskites. You all know about perovskites. At least one of you know about this. I just know that this gives owns its name to some Russian chemist Perovsky, and is found in some strange mineral in Siberia. And I guess from their title that they have something to do with the piezoelectricity. I don't know anything else. But I know what is the group. The group is not this. The group is more complex, but they have the same invariance as this one, and just ask for something to be invariant under reflection x, y, and z separately. And no, I'm sorry. I should actually, the group is more complex because I forgot to write it should also be invariant under permutation of the x, y, and z. Okay. So you have these 3 invariants, just the radius, product of 2 of them square, and the product of 3 of them. But this is of order 6, so we should go to order 12. This begins to be nasty, and indeed, if I write this up to order 12, I get 22 coefficients, which is a bit too much. And actually, the group D2H, which was discussed in Professor Longa's talk, has the same basic invariance, hence the same expression. I hope so. I checked, but I don't know if I checked well. So, Sergienko, Gufan, and Uratsdin were saying, okay, we don't need 22 coefficients if it's enough to have 6, which is still a lot, but it's much more reasonable. And these are the other terms that you need. So I will not make the computation explicitly. Luckily, I don't have time, so this is a good excuse not to make the computation. But they can be done, and they are done in my paper. Well, you will find then the reference 2004. And you find that actually, if you work along the scheme that I said before, we see that all the other terms are in the range of the L0 operator. So their claim, which they justified with the other consideration, can be justified on the basis of this. And the difference is that they had to be clever to give their motivation to kill the other terms. I don't need to be clever. Poincare has been clever enough for me. I can just be stupid, sit on my computer, compute matrices, and find what is the range of the operator. I'm stupid, but luckily I came after Poincare, so I can do something. And in this case, I can, well, this is the matrix. But then there was a problem with the Guffin paper. Namely, they worked at fixed values of the parameters. So I want to stress that if you have a phase transition, we can work in two ways. We can work at fixed values of the parameter and see what happened before the phase transition and after the phase transition. So we have two pictures and spot the difference game. Or we can make a movie, and we want to be able to follow what happens as the control parameters are changed. But in this case, I should be careful because some of the coefficients pass through critical values. You remember those A1 in the denominator before, or A2, or A1 plus A2, or maybe it was C1, C2, I don't remember. So the problem is that if we want to be able to work in a full neighborhood in parameter space, we need that the Poincare transformation are well defined in the full neighborhood of the critical point. In this case, of course, you will be less effective in reducing your polynomial. Now, this is just to mimic what Guffin and the others were saying. So, well, this is useful if you just want to look back at the slides in next week. But basically, this is that if you can write something like that, everything which is in the range can be killed. So you can eliminate everything which can be written in this way. These Q are the gradient of this, and these were the derivative, sorry, these were the gradient. These were the component of the L naught operator, and these are the gradient of the H with respect to the J, so you must have the cross derivative condition. So, two final notes. When I say in a sufficiently small neighborhood, this will work. What means sufficiently small? It means that I should be careful to this problem of the small denominator. Each step reduces the radius in which this is valid. If this is so small that I don't see the symmetry breaking solution, then I can just throw this out. This is of no use. But there is a good news, that when I make a concrete computation, the trouble comes from the small denominator. I just see the explicit formulas, order by order. So I can control what is the radius of convergence. If I want to make a theorem about the infinite series, then it's complicated. But if I want to make a computation up to order 12, I can read from my explicit formulas what happens. And finally, don't forget, I was stupid. I just made a change of coordinates. This is not the most general way of reducing the polynomial, because you could be a good physicist and know that there is some term which you can discard with no effect, that there could be a potential which is really different but has the same physics. So I am stupid, and I gave you a talk about the stupid way of changing this. Then you can, of course, use this combined with your clever physical intuition. And what is the conclusion? I think I am in time, yes. First conclusion, the Poincare approach is useful, constructive, even in this field of Landau, phase transition, maybe even in liquid crystal application of this. And second note, presumably this can still be improved. There is still work to be done to use the special feature of Landau and of the Landau potential that you meet in liquid crystals within these lines. So these are some reference on this. Okay, actually this can be done for Landau, Ginzburg, and gauge theory too. I didn't notice before, but preparing the talk for this conference, thanks to the invitation of David, I realized that this can be done even for gauge. And okay, in the slides you find some references, but the only relevant thing is thanks. Very on time.
Very good. Any questions?
I just wanted to make a comment which I don't know whether it's relevant to liquid crystals, but it is elasticity, and it concerns these representations in terms of an integrity basis. So from the point of view of analysis, they are a little bit less convenient than other representations because they drop regularity. So, for example, if you have a function of a symmetric matrix which is isotropic, or if you have so suppose you have a symmetric matrix and you have a function of it which is isotropic, then you can represent it, of course, in terms of the principal invariance of the matrix. So that's what this integrity basis is. Or you could represent it as a symmetric function of the eigenvalues. Now, the function of the eigenvalues has the same regularity as the original function, but the function in terms of the elements of the integrity basis drop in regularity. So certainly in elasticity, it's much better to use the symmetric function of the eigenvalues. This is just a...
Yes. On the other side, it should be noted that if you look well, you're thinking basically to some Lagrangian density which depends on gradients and so on. Now, there is this fact that if you go to the orbit space, then the symmetry stratification is coherent with the topological stratification, but also the dynamics follow this. So if you're basically the gradient along a singular strata is always pointing along that stratum, which means basically, I'm used to think of this in dynamics. You could think that you reduce to the orbit space, which is on this part, and then you could have something which goes like this, while before it was going like this. So you can develop a cusp. But this is not possible because the singular strata can be attained only as limit points. So it's true that you lose regularity, but it should also be true that if you look carefully, then you can split the problem in such a way to somehow recover it. And I don't know exactly about this, but when we made this work about gauge theories, basically we were able to do this exactly based on this remark. But there was some non-trivial intersection of orbit space theory, stratified manifolds, Sobolev spaces, and so on. So I tried to keep away from this. And I'm not sure at all that it could work in any other case. So maybe in elasticity there is no way.
Well, time's getting on. I'm sure we're all ready for coffee, so let's thank